Welcome back to Think Thrice Problem Solving. Today we're going to be solving a fun but challenging summation of a series problem. So this is akin to problems that you might have on math competitions at the senior high school or collegiate level. So we have a series here, and we want to find what this sums up to. And we notice that it's not looking like a series we've seen before. So maybe you want to be looking out for a common power series would be a good strategy. So that's your hint. So if you'd like to pause this video and give it a try, go ahead and do so. Otherwise, we're going to jump straight into a solution. So what we're going to do here is the first thing I'm going to do is I'm going to notice that I would really love to get rid of this term in the numerator. So this term 2n+2. It looks like it's pretty similar to that factorial on the bottom, and I know that that term is actually going to be in the factorial. So I'm going to rewrite this now, and what I'm going to do is I'm going to take this sum from n equals 0 to infinity of negative 1 to the n, and we're going to have 2n plus 2, but then I'm going to write the denominator, so 2n plus 3 factorial is going to be 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. Okay, so I notice right away I can cancel out these two guys. And I'm left over with just the sum from n equals 0 to infinity of negative 1 to the n over, I left an n out here, so this is 2n plus 3. And I'm going to have that over 2n plus 1 factorial times 2n plus 3. Okay, so I'm looking at this, and if you've spent some time around power series, what should we notice here? So if you're in a competition, you're looking at a problem like this, so a thing that jumps out, 2n plus 1. What is 2n plus 1 used to describe? So 2n plus 1 is actually all of our odd integers. Okay, so when we're counting up in n, these are all of our odd integers. So we're looking at this and we see negative 1 to the n over all of the odd integers. And what this is actually going to relate to, so this is very close to a Taylor series approximation of the function sine of x. So sine of x, if we were to break it out, is actually going to be equal to 1, over 1 minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and then minus for the next odd term, and so on. And I can actually write this as the sum from n equals 0. I guess I'll probably write it as n equals, yeah, that's fine, n equals 0 to infinity of negative 1 to the n times x to the 1 plus 2n, so our odd powers, divided by 2n plus 1 factorial. So when I'm just looking at this, this is pretty close. So this guy and this guy look like they might be cousins, a little bit related. There's a little bit different. What's the biggest difference? Well, so the biggest difference is this guy over here. So it's this guy over here and then this guy in the numerator over here. Okay, so but I could always, I don't know, choose an x value. So sine of x, if I just made that a 1. So the real problem is this 2n plus 3 term. So how on earth do you get a 2n plus 3 term in the denominator? So if you pause the video, you might be able to figure it out, but what if I had x times sine of x? So x times sine of x would give me the sum of n equals 0 to infinity. I'm just multiplying this thing times x. So I'm going to have x to the 2 plus 2n divided by 2n plus 1 factorial. So we see that 2n plus 1, what is that going to get me? Well, this is a little bit of magic, but if I was to take the integral from 0 to x dx of this guy, and then the integral of this guy on the right, let's do that. So let's look specifically at the right side. So the right side is going to end up being the sum from n equals 0 to infinity of, still going to have that negative 1 to the n, over 2n plus 1 factorial. So all that's just a constant. But then I'm going to have x to the 1 greater than that, so 3 plus 2n, divided by that exponent, 3 plus 2n. And this is starting to look really, really, really good. Okay, so now if we look back, we can see that this is almost exactly like this. And just like I said before, when is this exactly right like it? So it's exactly like it if x equals 0. So let's set x equal to 0, and now we're going to get the integral from 0 to 1 of x sine of x dx is going to be equal to the sum from n equals 0 to infinity, negative 1 to the n over 2n plus 1 factorial times 3 plus 2n, which is exactly what we're trying to find. So what did this boil down to? Now the question is, can we integrate this? And the answer is absolutely. If we got through from the stuff above this, we can do this in our sleep. So let's do some integration by parts. So u equal x, du equals dx, dv is equal to sine of x dx, and v is equal to negative cosine of x. So we're going to get uv, so negative x cosine of x minus the integral of negative cosine of x dx, which is going to be negative x cosine of x plus sine of x, and that whole thing is evaluated from 0 to 1. So negative 1 times cosine of 1, so we're going to end up getting negative cosine of 1, negative cosine of 1 plus sine of 1, minus 0 times cosine of 0, which is 0, plus sine of 0, which is 0. So our final answer is going to be this guy right here. So it turns out that that series is going to come out to exactly sine of 1 minus cosine of 1. All right, so I hope you enjoyed working through that problem with me. If you did, please like and subscribe. If you have an idea for a video, please submit it and you might see it in a future one. And as you're working through problems on your own, think once, think twice, and if you really get stuck, think thrice.